All right, so what we're going to do with the remainder of today is we're going to review a little bit about enantiomers, diastereomers, and mesocompounds because these are pretty tricky concepts. So the first one is enantiomers. Enantiomers, we said, are non-superimposable mirror images. They have the same physical properties. And the easiest way to identify an enantiomer is to take your chiral molecule and then flip all of its stereocenters. So flip them all from R to S or S to R, and you've drawn your enantiomer. Alternatively, you can draw a mirror image. Somebody was asking you, does it matter which plane you draw the mirror image on? No. You can draw a mirror image in front of you, to the side of you, behind you. It doesn't matter. As long as you're drawing a mirror image, you're drawing an enantiomer. The second one is looking at diastereomers. Diastereomers are connected in the same order, but in this case, they're not mirror images. And they have different physical properties because of that. Like I said, the easiest way to spot a diastereomer is to flip some, but not all of the stereocenters. So you can flip one or two, but you can't flip all of them. And then the last one to watch out for are mesocompounds. Mesocompounds are molecules containing stereocenters that are superimposable on its mirror image. The easiest way to spot these is that they have stereocenters, but they also have an internal mirror plane. That means that they're chiral. And if you try to draw the mirror image, you can, but you've just drawn the exact same molecule. So its enantiomer is identical to itself. So let's take a little bit of practice with this. But before I go on, I wanted to point out one point. There's an easy way to spot the potential number of stereoisomers. You go 2 to the n equals your number of stereoisomers. And n in this case equals what? Yeah, number of stereocenters. So in this case, n equals your number of stereocenters. But the thing to watch out for is some of these stereoisomers may be mesocompounds and they may be identical. But this is the most potential stereoisomers you can get out of a molecule. Yep?
Is that 2 something?
Yeah, it's 2 to the nth power. So 2 raised to the power of n.
Oh.
Yep. So the interesting thing with this is the more stereocenters you add onto a molecule, the more difficult it is to make. Obviously, if you're trying to make something enantiomerically pure, you could have 95% enantiomeric excess, and that's still problematic if you have multiple enantiomers in there. But let's do a practice activity here. Draw all possible stereoisomers for the following. The first one is 1 bromo, 3 chloro, cyclopentane. So I'm not telling you R or S. I want you to try to figure out all the potential combinations. And I'll give you guys a little running start here. So we've got 1 bromo, and then we've got 3 chloro. How many stereocenters do we have? 2. Which means how many potential isomers do we have? 4. 2 to the second power equals 4 possible stereoisomers. So let's try to draw all of them. How many of you guys think you got it already? All right, I'll give you guys a couple more minutes. I'm going to draw in my cyclopentanes just to speed things up. All right, so we've got our 4 cyclopentanes. What if both of these are wedges? That's one potential stereoisomer. What if bromine's a wedge? Oops. And chlorine's a dash? That's different, right? What's the relationship between these two? Diastereomers. We flipped one but not both stereocenters, so these are diastereomers. All right, let's continue on. What if we have the bromine as a dash and the chlorine as a dash? What's the relationship between these two? They're also diastereomers, right? We flipped one but not both stereocenters. And then what if we keep this here and this here? What's the relationship between these? Yeah, another set of diastereomers. Oh, thank you. Good catch. Trick question. So diastereomers. All right, but one thing people get thrown with is they say, well, aren't these two the same molecule? Are they? They're enantiomers. It's like our left hand versus our right hand. They're mirror images of one another, but if you tried to superimpose them, you can't. The other easy thing to notice is, in this case, the bromine went from a wedge to a dash, and the chlorine went from a dash to a wedge. So we flipped both stereocenters, and these are both enantiomers. All right, what about these two? Are they the same molecule, or are they different? What's the relationship? They are also enantiomers. We also have a few other sets of diastereomers. We could also say that these are diastereomers. There's a bunch more. The point is that with diastereomers, you flip some but not all stereocenters. And if you flip all stereocenters, then what you've really drawn is an enantiomer. Let's try one more. Okay, let's do 1,3-dimethyl cyclopentane. Let's draw all 4 possible stereoisomers. So we've got 1 and 3. How many stereocenters? 2. So we've got a stereocenter there, stereocenter there. So I'll help us draw these cyclopentane rings. We need 4 of them. You guys are going to get really good at drawing all sorts of polygons by the end of this class. So just like before, we could have our top one be a wedge, or we could have our bottom one be a dash, or we could have the top one be a wedge, and the other one be a dash, or we could have a dash and dash, or we could have a dash and wedge. Yep.
Should that one, are you sure that one would be a stereocenter? Because the upper one is attached to CHH and the other side is also CHH as well.
Yeah, so that's a good point. This is something that confuses a lot of people. If we look at this carbon, right? This carbon is bonded to a carbon, hydrogen, hydrogen. This carbon is bonded to 3 hydrogens. And then this carbon is bonded to a carbon, hydrogen, hydrogen. So we could say the carbon in the left and the right are the same. That means we have to continue going further along the ring. And if we go down here, we have to keep on going until we find a difference. This one's attached to a carbon, hydrogen, hydrogen. This one is attached to a carbon, carbon, hydrogen. So you see how we found the difference by continuing on along that chain? So if we were to assign R or S to this, what would it be? We would have first priority here because we've got the biggest difference, second priority here, and third priority there. Hydrogen's pointing back, so it would be R. That top stereo center would be an R. A little bit tricky. All right, so let's kind of go back and do the same sort of organizational stuff that we did before. I'm going to erase all of these. What's the relationship between these two? Yeah, diastereomers. Yep.
You erased that. Could you explain how the first one had 3 H's on the top?
Because it's a methyl group, it's CH3, so we're looking at that carbon. That carbon is bonded to 4 hydrogens, so it's HHH. Yep, we're looking at that carbon and comparing the attachments coming off. So these two are diastereomers. What about these two? Yeah, they're also diastereomers. And then we could say, all right, these two are also diastereomers. All right, let's go ahead and compare these two. Oops, sorry. Are they enantiomers? They're meso. So we can go through and we can say, all right, there's an internal plane of symmetry. So these are the same molecule. They are meso. So even though they do have stereocenters, they have an internal plane of symmetry. Therefore, they can't be considered enantiomers anymore. What about these two? Are these meso? No, they don't have an internal plane of symmetry. The only reason the one on the first one and the third one did was we had two of those methyl groups pointing on the same side. If we have them pointed on opposite sides, they're no longer the same molecule. So in this case, these would be enantiomers. So how many possible stereoisomers do we really have with this molecule? 3, not 4. So that 2 to the n really is the most potential possible stereoisomers, but you always have to watch out for meso compounds because occasionally you will be drawing the exact same compound over again. Does that make sense? All right. Let's continue on a little bit. And I did want to talk about cis versus trans diastereomers. So we've already covered this briefly, where we said if you've got a substituent or a substitution pattern that looks like this, is that cis or trans? Trans. The easiest way to remember is that the methyl groups are on opposite sides. One methyl group is sticking towards us, the other one's sticking away, so they're on opposite sides of the ring. You could name this using the R or S designation. Oftentimes people refer to things as cis or trans as well. Alternatively, we said if you've got two of them on the same side, this would be what? Cis. So cis could be both going into the board, both coming out of the board. They're very commonly used for cyclohexane rings. The important thing to remember is it can only be used when comparing identical substituents. So in this case, we could have compared the methyl groups because they're identical, or the hydrogens coming off of those carbons because they're also identical substituents. There's also another cis and trans out there with alkenes. What's an alkene again? Double bond. So let's say we've got this group. Do you think this would be called cis or trans? Trans. The easiest way to do this is to draw an invisible line going down your double bond. If we look at our hydrogens, they're coming off of opposite sides. So this would be a trans alkene. And then if we do the same thing but I draw this molecule instead, would this be cis or trans? Be cis. Both hydrogens are on the same side. We're comparing the same substituent. All right. Pretty easy, right? Well, yep.
If you're doing nomenclature for this cyclohexane and you're identifying both the stereocenter as well as the cis and trans, which comes first? Would it be like trans parentheses 1R, 3R?
That's a good question. I think cis comes before the stereochemical configuration, but I'll have to look that up.
Okay.
All right, what about this one? I'm going to draw a molecule out. Oh, sorry. Is this cis or trans? It's neither. We don't have identical substituents coming off of either side. So this is neither cis or trans. But this molecule is different than this molecule, right? I'll draw this one out. What if we put the fluorine up and the methyl group down? Those aren't the same molecule, right? They're isomers. So now we need to learn how to name things using a little bit different nomenclature than cis or trans, because this simply doesn't work anymore. So what we do this time is we compare these. And so what's higher priority, chlorine or hydrogen? Chlorine. So what we'll do is label this as our higher priority. What's higher priority, our methyl group or our fluorine? Fluorine. Remember, fluorine is heavier than carbon. So again, we would label this as our primary methyl group. So it looks like we've got the same group on the same side. Instead of using cis or trans, we refer to this as Z. You guys want to know my trick for remembering these? Yeah? It's German for Zusammen, if you speak German. Am I pronouncing that right? Zusammen? Yeah. So I always remember it as the same side, right? It's cheesy but super effective. If you go through and designate it here, now we've got the same priority on opposite, or highest priority on opposite sides. I don't have a good one for this, sorry. This is just E. So we've got E versus Z alkenes, and we can use this when we've got substituents that aren't the same going off of the ring. And we're going to cover this quite a bit when we get into our alkenes chapter, but I did want to present it before we get there. Easy enough? Yeah? Some of you are like, no. Yeah, just like with RRS, this would come first. So let's actually do this bottom one and let's try to name it, just for fun. All right, what's the longest chain? 3, right? The methyl group's got a carbon coming off of it. So this would be E, 1 chloro, 2 fluoro, prop, right? Because it's a 3-carbon chain. And then to designate the double bond, we would normally have some sort of numerical operator in there, but we can actually just say propene because it's implied that it has to be on one of those 2 double bonds. We'll go into alkene nomenclature in much more detail when we hit that chapter, so don't worry too much about this right now. All right, let's continue on. There's one last thing I want to show you guys before we leave chapter 5. And I feel like I have to show it to you, although we won't see it again until 3rd term. And this is referred to as the Fischer projection. Fischer projections are a shortcut way of drawing dashes and wedges that are really common in carbohydrate chemistry. So let's take a look at why maybe chemists use this for carbohydrate chemistry. This is D-glucose. Those of you that are taking bio or have taken bio are quite familiar with D-glucose. D-glucose is kind of a pain in the butt to draw, right? It's got 4 stereocenters. You've got a lot going on that you've got to keep track of. So the Fischer projection is a shortcut. And with Fischer projections, what you do is you assume all horizontal lines are wedges. And then all vertical lines are dashes. All right, so let's take a look at an example of a Fischer projection. Let's say I draw one that looks like this. We're shortcutting it and we're not drawing dashes and wedges. This is our Fischer projection. How would we draw this using bond line formula, using dashes and wedges? Yeah, it's a little bit weird to think about. But this hydrogen is horizontal, so it's going to be a wedge. This alcohol is also a wedge. This ethyl group, on the other hand, is going to be a dash. And this methyl group is going to be a dash. So this would be bond line. All right, so let's assign stereochemistry to this. Is this R or S? You guys want me to draw it a little bit differently? So imagine this is the top down. Let's change this to our side view. So over here we've got I'm going to flip it on its side. So this hydrogen's now sticking out there. We've got an OH. Now we've got an ethyl, and we've got a methyl. So can you guys see how I took this and I basically twisted it like that? Can you guys see that? That makes it a little bit easier to see the stereochemistry, right? So what's going to be highest priority? Oxygen, followed by what? Ethyl, followed by methyl. So is this going to be R or S? S, because the lowest priority is pointing forward. So we need to flip the R and S. So this would be an S stereocenter, and this one is also described as S. It's a little bit weird to think about, but the analogy I really like from mastering organic chemistry that I'm going to show you guys is the cat analogy. All right, so imagine you've got your cat, and your cat has a head, right? And then down here, your cat has a tail. And then over here, you've got a foot, a foot, a foot, a foot. This is the tummy view of the cat, right? If you're a cat laying on your back, you've got your paws sticking straight up, your head back, and your tail back. It's kind of the same as a Fischer projection. So the horizontal lines are coming towards you just like a tummy view on a cat. It's super cheesy, but I like his cat analogies. I have like 4 cats on occasion, so I'm not super weird, I promise. So if you do the side view, what you really have is your cat head. You've got a foot going out like this, foot going back like that, foot going out like that, and foot going out like that, right? I'm not going to even attempt to draw an actual cartoon cat. All right, let's do an example with D-glucose.
Can you just move back a little bit?
You guys like my cat analogy? All right, with D-glucose, let's draw the Fischer projection. CH2OH. This is significantly easier than drawing all of those dashes and wedges for most carbohydrate chemists. The stereochemistry hasn't changed at all, but we're kind of doing the tummy view of D-glucose, right? So let's do our side view. And the side view I like to show, it essentially curls around. And on this side, if we're looking at these carbons, should the hydrogen be a dash or a wedge? So imagine I'm taking this and I'm twisting it like this so that it's rotated and curling back. This hydrogen should be a wedge, right? It's going to be coming out to our left-hand side. So you've got a hydrogen sticking out here. Got a OH going back. The next one, we've got a OH sticking out here. Hydrogen going back. Next one, we've got a hydrogen coming towards us. OH going back. And we've got a hydrogen here. And an OH going back. So if drawing it on the side-on view is easier for you, you can easily transpose these. But the key thing that we're doing is we're taking this and we're twisting it like this. The main backbone is curved back like a hook. And then all of the substituents are coming out towards our eye. So you can imagine that with our eye view, we're kind of looking down this way. So on sapling, you may have some questions with Fischer projections. We're not going to delve too deeply into it until we get to the carbohydrate chapter, but I did want to present it because it is a valid way of showing stereochemistry. All right, if you've got Tuesday lab, remember that we do have lab today. It's the extraction lab. Wednesday lab does not have lab this week, and then Thursday and Friday lab, you do have labs. You're doing the essential oil lab this week. All right, I'll see you guys tomorrow or in lab.